All right, let's get started. Today, we're going to pull back the curtain on what it really takes to engineer the brain of a modern micro EV. We're talking about the Vehicle Control Unit, or as we call it, the VCU. This is the central nervous system of the whole machine.
So, what does it actually take to build one of these? Well, the very first thing I tell my engineering teams is this: throw out everything you think you know about this class of vehicle. Seriously, we are not just making tiny cars anymore. The game has completely changed.
Look, the days of just grabbing some off-the-shelf golf cart parts, they're over, completely gone. That whole approach of using simple industrial controllers is frankly a relic. Why? Because the market demands more, and more importantly, a whole new wave of global safety rules makes it absolutely non-negotiable.
What we're talking about now is pure global systems engineering. It's a high-stakes game, really. We're tasked with creating a super sophisticated powertrain domain controller, one that can go head-to-head with anyone, anywhere in the world. So, with that in mind, let's really dive in.
Okay, so here's our game plan. We'll start with the big picture, this quiet revolution in the market. Then we'll navigate the global regulations, lay out the architectural blueprint, get into the software, the soul of the machine, and finally talk about how we get from design to actual production.
All right, Section 1, a quiet revolution. Let's start with the why. Why is this so incredibly critical right now? Well, it's because there's been this quiet but massive shift in micromobility that has totally changed the game.
You know, it's really been a night and day transformation. In the past, the controller was, well, it was dumb. It was basically a glorified on-off switch for the motor. But today, the VCU is the brain. It's a full-on powertrain domain controller packed with functional safety and modular software. It's a completely different beast.
So here's the bottom line, the key takeaway. These three standards you see here, ISO 26262 for safety, AUTOSAR for software, and ISO 16750 for environmental testing, this isn't a nice-to-have list. This is your ticket to the game. If you don't meet these, you're not just at a disadvantage, you're not even allowed to play. You literally cannot sell your car in any major market. It's that black and white.
Okay, on to our next section, the global regulatory gauntlet. And I call it a gauntlet for a reason. This is where we get into the nitty-gritty of how a minefield of different rules around the world directly forces our hand in VCU design.
This is fascinating. You can see two completely different mindsets at play here, and they lead to totally different engineering problems. In Europe, they're obsessed with anti-tampering. They don't want people hacking their cars to go faster, so the VCU has to play detective. But in the US, it's all about liability. They're worried about someone coasting down a steep hill and breaking that speed limit. So the VCU has to be a proactive enforcer, using regenerative braking to hold the car back.
And if you thought that was tough, just look at China and Japan. They are pushing the absolute limits. In China, with their intense focus on battery safety, the VCU can never fully power down. Even when the car is parked, it has to sip power to monitor the battery. It's a 24/7 guard. Then you've got Japan. The VCU has to be smart enough to realize, hey, the driver just slammed the accelerator, but there's a wall 2 feet away. This is probably a mistake, and it has to override the driver. Incredible, right?
Okay, so we've mapped out the regulatory minefield. Now, with those boundaries clear, we can start architecting the VCU itself. Let's get into the blueprint. The very first fork in the road, the biggest architectural decision you have to make, is voltage. And it's a classic engineering trade-off. Do you go with a 48-volt system? It's cheaper, it's touch-safe, great for city cars. Or do you need highway performance? If you do, you have no choice but to step up to a high-voltage system, 350 volt or more. And trust me, that's a whole different world of complexity and cost. And if you want a perfect example of that high-voltage complexity, look no further than the HVIL, the high-voltage interlock loop. Think of it like a tripwire. It's a low-voltage safety circuit that's daisy-chained through every single high-voltage component. If that loop is broken for any reason, a connector comes loose or in a crash, bam! The VCU has to cut all high-voltage power. And it has to do it almost instantly. So here's my direct strategic recommendation for any team that's just getting started. Go with a distributed architecture. That means you have 3 separate boxes: the VCU, the motor controller, and the battery management system. Why? 2 huge reasons. 1, it de-risks your development. And 2, and this is critical, it gives you supply chain flexibility. You don't get locked into one single supplier. You maintain control.
All right, Section 4, the software soul. You know, the hardware is the skeleton, it's the foundation. But the software, that's the personality, the intelligence, the very soul of the vehicle. This is where the magic really happens. Now, to handle all this complexity, you can't just code directly on the bare metal anymore. That's the old way. Today, you absolutely have to use a standardized architecture like AUTOSAR. Think of it like an operating system for a car. It separates your application code, the stuff that defines how your car feels to drive, from the nitty-gritty hardware underneath. It's a game changer for making software that's modular and reusable. Okay, this is probably the single most important piece of software logic in the entire VCU, torque arbitration. You can think of it as the ultimate pecking order for power. And here's the key. The driver is at the bottom of that list. Your foot on the accelerator pedal, that's just a request. It's the lowest priority. If a safety system kicks in, it gets top priority and can instantly command the torque to zero. Safety always, always wins.
Then you have the limp home matrix. This is how the vehicle protects itself and, more importantly, you. If something goes wrong, the car doesn't just die and leave you stranded. No way. It gracefully reduces its performance. First, maybe it cuts the AC and limits your speed. If things get worse, it enters what we call turtle mode, just enough power to safely get you to the side of the road.
Okay, last section. We've designed it, we've coded it. Now, how do we actually build it? Let's talk about bridging that huge gap from the blueprint to mass production. All right, the first and biggest production question is always make versus buy. And my advice for almost anyone who isn't a massive global OEM is to go with what we call a gray box model. It's simple. You buy the hardware from a trusted supplier, but you own the application software. That software is your secret sauce. It's your IP. It's what makes your car unique. And this chart right here is why that buy the hardware strategy makes so much sense. It surprises a lot of people. You'd think the powerful safety microprocessor would be the most expensive thing, right? Not even close. Look at this. The housing and connectors can easily cost a quarter of the total. That rugged aluminum box, those waterproof, vibration-proof connectors, that's where the money goes.
And of course, before anything goes into production, it has to survive the trial by fire, the validation plan. This is the final exam, and it is brutal. We do things like intentionally try to fry it by jump-starting it with a 24-volt truck battery. We freeze it down to -40 Celsius and then bake it up to 85 over and over. It has to pass everything before it ever sees a real car.
So if you take one thing away from all this, let it be this. This isn't about simple on-off switches anymore. The era of the simple controller is dead and buried. What we're doing now is complex systems engineering, plain and simple.
And that leaves us with one final big question to think about. As our cities get more crowded and these little micro EVs become more and more important, is the fight for the brain inside these cars the next major battleground in the auto industry? I think it just might be.